Now we will talk about perceptron. And perceptron as such has been proposed in 1957 by Rosenblatt. So it's a really old thing that was first implemented as analog electronics. So it was really dealing with some discrete components, basic discrete components to build up some kind of circuit, electronic circuits that was simulating somehow a neural network. I would even say a neuron, basically. So this is considered as the simplest neural network we can think of. And this perceptron is a linear discriminant. And it consists to what we saw before. It is exactly the formulation that we had before. We just make one change here. You can see that we use W transpose X, which is totally equivalent to the summation of Wij xj. So transforming the transpose, the product of W transpose and X is equivalent to making the sum over H components. And the perceptron is making the same kind of assignment. If H is positive for a given X, it is C1, otherwise it is C2. So coming from that, I would say linear discriminant model, the perceptron has some specific elements. It is basically, these elements are there to define the W0 values to use for a given data set. And so this is based on an optimization. So remember that in machine learning, supervised learning, everything boils down to having some kind of model and having some parameters represented in some kind of structure, and where we want to optimize the parameterization of our model H according to some criterion. And so here our model is that thing, is really a linear discriminant. So we are optimizing the W0 here according to the Perceptron Criterion, which is specific to what was proposed. Maybe not exactly like this, but it comes to that rule in terms of implementing a perceptron. And we assume here we need to be cautious. The RT, the labels are either -1 or 1. If we are not using the 0, 1 notation, we need to use the -1, 1 notation to make it working. To be sure it is working well. It is working as expected. And so this E-pers, it is basically the perceptron criterion. So it is an error measure. That error measure is consisting of summing over all misclassified X's minus sum over all misclassified samples, the product of label RT and the HX of T. So we are making the product of R and H for a given X. So we are HXT times RT, and we are summing this product for all samples that are misclassified, because Y here, the set Y here, is the data that are not well classified by H. So all well classified data are not used in that sum. And so we define H more formally, it is a set. So basically it is defined as a set of all samples in our training set X, such that, the vertical bar here is saying that such that RT times HXT is negative. When it is negative, it means that the sign of R and H are different. And so when the signs are different, we are in a case of a misclassification. If the product of R and H was positive, it would have been a correct classification. So we take out all the samples in our training set that are misclassified. And now we have a criterion, but we need now a way to figuring out the values of W0 to parameterize our model H in order to minimize our error criterion. So mathematically speaking, we have this error function here. We are using an argument, so we want to optimize over this function E, such that we will get the W0 that are minimizing E. So we get this W0 that are minimizing that function. And these one are written here as the W star, W0 star. So we aim at finding out the parameters that are minimizing our error criterion. For achieving this, we are making use of partial derivatives. So we are taking the gradient of that function E according to the W's. So this gives us a vector of d plus 1 dimensions. So we have one derivative for each of the parameter, including the W0, which is the constant, and the D parameters, which are the element of the vector W here. So we are making the partial derivative of function E according to these. And from that, we will make a small modification of the weights. So the weights Wi, including W0, will be modified, and we will modify it by moving them, by changing them in the direction opposite to the gradient. Because when we get a gradient, if we move up with the gradient, we will move in the direction to increase the error. So we want to minimize the error, so we need to go down. We need to do the descent of the gradient, going in a direction opposed to the gradient we obtained for all the parameters. So basically, we have a rule that is updating, making a small update to each of the parameters by adding them delta Wi. So we have Wi, current Wi plus a delta that gives us the new Wi. And that delta Wi is defined as minus eta. This is a parameter, the step size, times the partial derivative, which is the element of the gradient according to variable I. And this for I from 0 to d, so we have d plus 1 parameters to optimize that way. And as such, the step size, the eta parameter, is between 0 and 1. So we often call this the learning rate. So at which rate, what is the amount, what is the step size we are making at each iteration? So if we are using a really small, very small value, we are looking to make this in the direction of the gradient, but a small step allows us to somehow not move too fast, not move too far away, because the gradient is a measure that we are obtaining locally. We are not, we have a really local view, I would say a myopic view. So making a small step allows us to be relatively safe in terms of the update, but that may mean to make many updates. Conversely, if we are going with a big step size, we will have the possibility of making a too big step, and the gradient may change because what we see locally may be different at greater distances from the current point. So looking at a function here, think of that function as being some kind of valley shape. You know, we want to get in the middle here. This is where the value is minimal. This is where the error is minimal. If we see that it's having a kind of valley with over representing the error function. When we are starting here at x0, we are starting at a relatively high error values, and we see that I would say the gradient is really in that direction here. This is not true. It is in fact going in that direction. This is the direction of the gradient according to the partial derivative. But given that we are doing gradient descent, we will move that way. And as such, we are making, you know, here we see the step between x0 and x1 that is corresponding to our step that we are taking here. So it's here we have the theta minus eta, sorry, not theta, minus eta times the partial derivatives that get us to the x1, and we apply this. And here at x1, we see that the gradient has changed slightly because we move in the space, and the direction of the gradient is not exactly the same. We expect it will change smoothly, but you know, moving at bigger steps may get us into bigger changes in the gradient direction. And so we've got from x1 to x2 here, and likewise we've got from x2 to x3 here, and then we get from x3 to x4 at that point. And if we continue, we will eventually converge toward the minimum in that position. So this is the principle of gradient descent. So if we are looking at another example in 3D, so we see we have this kind of shape. It may look like some kind of real environment, but it is really a mathematical space. So we have that shape, and we want to get our points at the minimum. So we have 3 points to start with. We have that one, and that one, the 3, I would say, black dots. And you can see them as small balls that we want to get them to move to the lowest position in that space. So as such, and we will move the 3 balls simultaneously for the sake of that example. So we see here that we are making a first step, and as such, they move in different directions. So we see that one moved from the original place to somewhere more on the left. Likewise here, and here it has moved in a position that we don't see because we have the small bomb that is hiding it from our point of view. Second step, we have that thing. Third step, we move even further. What we can see is that one here is moving fast because the slope is kind of important, while that one here is moving quite slowly, and here it's even more slowly. So these are moving relatively slower when they are in a position where the gradient is relatively small, and of course, when the gradient is more important, it is moving faster. Another iteration, and yeah, I think this is mostly it. So we've got into this position. What we can see here is that these 2 points get to about the same position. Maybe the second one, that one here, will take some more time, but eventually we'll reach the same point, which according to our sample of the space, appears to be the global minimum of our space, at least in that domain. While the third one converge to that position, which is locally minimal, but it is not the global minimum. So the point here to understand is that with gradient descent, we don't necessarily reach all the time the optimum, the global optimum. We reach, I would say, depending on the type of model we are dealing with, some kind of local minimum, which may be okay, but is not necessarily the best configuration we can obtain from that given model with these parameters for a given task and error value. So here we see that, in fact, it reached the same point in the end. So now, if we are going back to the perceptron, we are kind of repeating here the perceptron error criterion that we are using, which is exactly what we saw before. We are summing all misclassified samples, and we are summing, in fact, the product of the RT, which is either -1 on 1 times the value of H. So basically, RT is giving us a sign, and that sign is usually the difference from H. And so the fact that RT times HXT give us necessarily a negative value because this is the criterion to be in the set of misclassified samples. We also have the minus sign that is canceling this. So this gives us some kind of error measurement. And what we do here is that we are calculating the gradient on from that error criterion. That partial derivative goes that way. We have partial derivative of E according to WI, which is basically computed on that according to WI. And as such, we care only about one element. So basically, we kind of get rid of all the RT, XIT, except the one that we care, because this is a sum, this is a sum with a product of R and X. And if we expand H, R and H of X, sorry. So if we expand H, which is this linear discriminant, we reach to that value. You can just make the developments on your own. This is relatively straightforward. And likewise for W0, which is this thing because we are not multiplying the value W0 with some component of X, then we reach the minus summation over all misclassified samples, RT. So these are the gradient values for WIs, including W0. And as such, implementing this into gradient descent, the modification to make at each step, the delta WI correspond to directly eta times the summation of our misclassified samples, RTXIT for WI, and for W0, it's basically eta summation of RT for misclassified samples. So this is relatively straightforward to implement, and that rule was implementable even with analog electronic in the 50s. So that's kind of simple. And if we get back to some kind of general algorithmic formulation, the perceptron algorithm looks like that. So we first need to initialize the weights to some kind of values to start the algorithms, because we are doing gradient descent, but we need a starting point. Simple rule is basically to assign the weights to 0. All the weights are set to 0 to start with. And from that initial set of initial values, we are applying gradient descent until convergence or until a maximum number of iterations, for example, by modifying each wj here, so each element of the variables from 1 to d, according to that rule, and the w0 according to that rule here. And we are repeating this. So we are modifying wj, w0 consecutively according to each samples, according to the set of samples that are misclassified by our model. So let's get with an example of with the perceptron, which is what we call a linearly separable example. So we have here 6 samples, 3 blue stars and 3 red crosses. And we want to figure out the classifier, the model, the linear discriminant model that is able to classify these samples well. And we will do this with the algorithm we just saw using the Perceptron error criterion. So at first, we don't even see here the separating plane line because it is off the domain. But what we can get is that all these 3 red crosses are circled in a black circle. That means that they are misclassified. So everything here is classified as a blue star. At the second step, now we see here with that line, this is basically the placement of the linear discriminant after 2 iterations. So we just applied 2 iterations of the gradient descent and we got into that configuration. What we can see is that that plane is somehow assigning everything here has blue stars, everything there has red crosses, and that one seems to be on the red crosses side. So from the 6 samples, we have 2 misclassified samples, these 2 blue stars. At the next step, we are making an update with gradient descent. Now we go from 2 to 1 misclassified samples. This one here. So everything on the right side is assigned to the red crosses. Everything on the left side is assigned to the blue stars. So we are making 1 mistake over 6 samples, 1 error. At the iteration 4, we have a new update, and then that's good. We have a separating hyperplane, and everything is correctly classified. The 4 red crosses are well classified. Likewise, the 3 red crosses and the 3 blue stars are also well classified. So what we know about Perceptron is that it is converging on linearly separable data. So we have some mathematical proofs that demonstrate that it is working well. Given enough iterations, it will converge to a configuration where all samples will be properly classified, assuming that they are linearly separable. It means that with that linear data per plane or that line in 2D, there exists a configuration where all samples will be properly classified, correctly classified. But we don't know exactly if usually there are many positions possible. You know, it's not just one configuration, except in some special cases. In most cases, you know, we have many placements possible with an error of 0 in that space. And the perceptron approach will not figuring out that particular configuration. It will just reach one configuration with 0 error, and that's it. It will stop them. It will not make any further updates to the weights of the model. However, for non-linearly separable data, which is for most of the real-world cases, there are no convergence. The perceptron is unable to deal with them. It is unable to correctly classify, to even learn something that will work well. So it is diverging on that. Why? Because somehow the error criterion that we are using, you know, the fact that we are summing for all misclassified samples, the product of RT, which is -1 and +1, times H of X, this is only weakly related to the nature of the errors. You know, we are not looking at, I would say, is the error big or small, and do we want to get some kind of space? Are we favoring some kind of configurations? That there's nothing like that in that criterion. It is basically a criterion that is looking to get correct classification. It is just computing the well classification here. The value of H is not directly related as is with the error that we are making. For a simple example here, we have only 4 samples. We have 2 red crosses and 2 blue stars. So you can see here that with these 4 samples, it is an example that is not linearly separable. You know, there are no possible placement of an hyperplane here of the separating line, straight line, of course, that will allow us to get an error of 0. You know, there is nothing. We always, the best case is to make one mistake. We will misclassify at least one of these 4 samples. So whatever we are cutting that way, or that way, or that way, or that way, any configuration will not achieve an error of 0. And with such case, the perceptron will have a hard time. And you can see here, after 20 iterations, we are already at 20 iterations, it is misclassifying the 2 red crosses. So it is basically assigning all the samples as blue stars, because everything on that side of the hyperplane is assigned to the blue stars. We can see that this is really not the best solution. Iteration 40 is kind of similar. It is even worse. It is assigning, it is making a mistake on all samples, because it basically says that that region is for the blue stars and that region is for the red crosses. So it is misclassified that thing because it is just over the separating line. And these 2 blue stars are also misclassified. Only that sample is well classified. And it can go on, you know, iteration 60, it is the same. 80, it is the same. So you can see here that it is not converging at all. It is in fact somehow dancing. You know, in the configuration, it is making some kind of dance, always going from one configuration to another, because, you know, the link is not clear between the error and the sample. So the perceptron somehow is a good starting point to understand or maybe see how we can apply gradient descent, but in practice, it is not working well. It was in fact one of the first model proposed for doing machine learning. It was interesting because it was based on what we knew at the time on how the brain is working, but in terms of relevance now in 2021 and 2020s in general, it is not anymore relevant for practical purposes, but it is good to kind of understand first model based on that and how it works.